Okay, bonjour. Bonjour. Buongiorno. Good morning. So, we're going to finish today the discussion of vector calculus. So, last time we introduced the curl operator in 3 dimensions, and we will finish today with the last operator in vector calculus, which is the 2-dimensional curl operator. So, we got a curl operator in 3 dimensions, and you remember this operator takes a vector field and produces another vector field in 3 dimensions. Now it turns out there is also a curl operator in 2 dimensions. This curl operator is actually it's lesser known than the 3-dimensional operator. Nevertheless, it's important in many physical models. So the first thing we remember, the curl of a 2D vector field is a scalar field. That's the first thing. We write this as curl, taking a vector field, taking another vector field. And what it does is, the vector field has got 2 components, f1, f2. And the scalar field that we obtain is combined as follows. You take the x1 derivative of f2 minus the f2, the x2 derivative of f1. That's the definition of the 2-dimensional curl operator. Okay. Similarly to the 3D curl operator, there are different ways to justify this. And I think the most memorable way of justifying this formula, to have an idea where this formula comes from, is actually by going back to the 3-dimensional curl operator. Let's imagine we have got, this is displayed below, a formal justification for the 3D curl operator. Formal justification using the 3D curl operator. So, we've got a vector field in 3 dimensions, but the third component is 0. So actually it's you could say it's a 2-dimensional vector field that we just extended to 3D. So we have got component f1 and f2, and the third component is 0. Okay, given that vector field, we apply the 3-dimensional curl operator. We just take the formula for the 3D curl operator and apply it, and just see what happens. Then you observe the following. The first component is x2 derivative of f3 minus x3 derivative of f2. And here, f3 is just 0. The third component is 0. So what happens now in the first component is, well, the derivative of 0 is 0, and f2 does not depend on f3. So it only depends on f1 and f2, on x1 and x2. So these guys are all 0. The third component is 0, and for the other guy, the x3 derivative vanishes. Something similar happens now in the second component. f3 is 0, so that derivative certainly vanishes. That is 0. And the x3 derivative of f1 is also 0 because, well, f1 only depends on x1 and x2. It does not depend on x3. There's no x3 going in there, so that one vanishes as well. Which means the only thing that remains is the third component, which is the x1 derivative of f2, del 1 f2, minus del 2 f1. So, and basically we've got a 3D vector, but only the third component is anything interesting. The first 2 components are always 0 in this case. And that, we take that as a justification to define this 2-dimensional curl operator. Okay, let's do one example just to see that in action. Again, we have a vector field let's say it depends in 2 dimensions. It depends on x1 and x2. The first component is a1, which is given by exponential of x1 squared times x2. And let's say the second component, a2, x1, x2, is given by, let's say, the sine of x1 times x2. So just a very standard vector field with 2 components. And if you apply the 2-dimensional curl operator, okay, the curl of this vector field A, we just apply the formula, and we get del 1 A2 minus del 2 A1. Just plug in the formula. And then what we get, okay, the del 1 derivative, del 1 of A2, that's cosine x1, x2 times x2. That's very clear. And then the del 2 derivative of A1, well, the only thing that remains is then exponential of x1 squared. That's the only thing that remains. So that is the formula then for the 2-dimensional curl operator. That is the 2-dimensional curl of this vector field. In fact, also the 2-dimensional curl operator has got some geometric interpretation. Let's briefly discuss this, as with another example. Let's again take this vector field that we've seen before, this rotational vector field. As a reminder, this vector field looked as follows. Basically, we got this rotational flow, which gets smaller towards the origin. And the further away you get from the origin, the faster the flow becomes. Okay, this vector field in 2 dimensions is given by f of x1, x2 equal negative x2, x1. And if you just apply straightforward the curl operator in 2 dimensions, then it's straightforward. Okay, we get the x1 derivative of 1 minus the del 2 derivative of negative x2, and of course the result equals 2. That's a very simple example, also illustrates again some physical or geometric feature of the 2-dimensional curl operator. Namely, the 2-dimensional curl operator is positive when the vector field rotates counterclockwise, and it is negative if it rotates in the opposite direction. In that sense, this curl operator expresses whether this vector field in 2D represents a circulation or a rotation. It tells you how much of it is a rotation. In fact, before we get to, let's first have a look at this picture here. So again, we have got a vector field. It's the same vector field we have already seen last time. And it doesn't really matter what precise formula it is. But just taking a look at this vector field, you can already identify a few areas where you have got a rotation. So for example, if you take a close look, it seems like here we got a rotation in the counterclockwise direction. So we would expect the vector field to be we would expect the curl of this 2D vector field to be positive. By contrast, in this region, it looks like the vector field rotates in the clockwise direction. So we would expect the curl of this vector field to be negative. So just some geometric intuition here. And indeed, if you compute the curl operator of this vector field and plot it with the nice colors, then you get this nice picture. So around the area where we have got this counterclockwise rotation, we observe that indeed the curl operator is positive. We get a positive component. And in the other area, where the rotation operator, where the curl operator is blue, we have a rotation in the clockwise direction, just corresponding to this visual intuition that we've seen before. Okay, so up to now we've seen the 2-dimensional curl operator, we've seen the formula, a few examples, and we have got a graphic. So we have got some visual intuition what the curl operator in 2D looks like. I would like to finish now the discussion coming back to the 3D curl operator. Because I think the curl operator in 2 dimensions arguably is easier to understand than the 3-dimensional curl operator. There's one more slide about the 3D curl. So what is the physical meaning of the 3-dimensional curl operator? Imagine we fix a small ball in space. So the position of that ball is fixed. It cannot move at all, but it can rotate. It will never move the position, but it can rotate. Now, suppose this ball is subject to a flow. It might be wind, maybe it's immersed in water, it might be subject to the flow of some fluid around it. Then this flow will typically put the ball into some sort of rotation. It cannot move, but it will somehow start to spin according to the flow. And what the curl operator tells you, if you have this vector field F, which describes the flow, then the curl operator tells you the axis and the orientation of the axis and the speed of the spin. Maybe one picture. So imagine you have this very small ball. It's subject to a flow. It's somehow immersed in a current. This very small ball, will start to spin around some axis. The curl operator tells you the direction of the axis, tells you the direction and the orientation of the spin and the speed of the spin. You could say that's a physical interpretation of what the curl operator tells you. We have seen the gradient earlier. That was very simple. It's just the derivative. We have seen the divergence. We've seen also the Laplace operator, which can be written as a combination of the divergence and the gradient operator. And we've seen the curl operator. The curl operator exists in 3D, but it also has got a 2D version. And okay, these operators are quite important, so let me finish with an outline of some topics in vector analysis. Basically, okay, what is vector analysis? We have now all these topics in place to start discussing vector analysis. And generally speaking, vector analysis is analysis using the gradient, the curl, and the divergence. That is called vector analysis or vector calculus. Or vector calculus. If you like. And generally speaking, many laws of physics are stated in that language. So I mean, every law of physics can be stated in many different formalisms, like differential geometry, but in practice, in particular for engineering purposes, you usually use the language of vector calculus or vector analysis. And let's just using what we have, let's just have a look at 2 examples. So there are Maxwell's equations. In the setting of Maxwell's equations, these equations describe, it's a system of partial differential equations which describes the evolution of electric and magnetic fields in space. And with some simplifications, you can write it down as follows. We've got the electric field E. E is the electric field. And B is the magnetic field or magnetic flux. Let's call it magnetic field for the time being, for simplicity. Physicists might object, but for simplicity, let's call it the magnetic field. Now, we've got a bunch of differential equations here. The divergence of the electric field equals the electric charge. So we've got one equation that uses the divergence. The divergence of B equals 0. And then we've got the following relations that involve the curl operator. The curl of the electric field equals negative time derivative of B, and the curl of the vector field B equals the time derivative of the electric field. So you got these two vector fields. You know that they have some divergence constraint. They have some divergence property. And also via their curls, they're coupled together. And that describes how the electric and magnetic fields evolve in time. And then that is a system of partial differential equations and vector fields. And on the right, you see a much simpler partial differential equation, which is very prototypical. It's a Laplace equation or a Poisson equation. If the right-hand side G is 0, you call it Laplace, but generally speaking, you call it the Poisson problem. There we are given a scalar field G. So it's a given scalar field. And we're searching for another scalar field F, such that the negative Laplacian of F equals G. The Poisson equation has many different applications. You can connect it to the heat equation. You can connect it to wave equations. You can connect it to diffusion problems. In fact, you can connect it to gravitational fields, and in fact, you can also connect the Poisson problem to some topics in electromagnetism. For example, F might describe the so-called electric potential, which is something we come back later in a few weeks. We come back to that later in a few weeks. Okay. That's also basic ingredients for vector analysis, and it has also been a warm-up to discussing vectors. So certainly we will in the next few weeks also again we will time and time again talk about vectors, scalar products, dot products. We will talk about the gradient, the curl, and the divergence. And the next topic, in fact, will be curve integrals. So basically, we take lots of tools that we have had in analysis 1 and 2, and now we generalize it to a certain geometric setting. That will be the topic of the next slides. Are there any questions right now about vector calculus, about this introduction? Okay, nothing urgent. Then let's switch. So in the meanwhile, I've switched from PowerPoint to Apple Keynote because I think that is more amenable for a presentation. Okay, so the topic of the second week, the main topic of the second week, are curves and curve integrals. If you take any class in physics, at some point you encounter curves and curve integrals inevitably. So an outline, what we want to do is as follows. Generally speaking, it's about integrals. We will integrate both scalar fields and vector fields along curves. So what we want to do. Okay, we remember integration in high school. So that's quite standard. We have an integral from a to b. You all remember that. We integrate a function, fx. And generally speaking, we want to integrate f over some interval from a to b. And that's our conceptual starting point. Next, we want to generalize this. Namely, we want to generalize that in the following direction. Instead of integrating over an interval, we now integrate over a curve. Of course, we need to settle what is a curve actually. And what does it mean to take an integral of some function over a curve? Okay, that symbol, which we will discuss later, means integration of f over a curve. So basically, we have got a curve in space, which we can visualize as follows. We have got some starting point, gamma A, and some start endpoint, gamma B. Those are all points on a curve, which we call gamma. And this curve is parameterized. So we've got some starting point A. And every point on the curve we can associate with a certain parameter. We start, like, given position A gives us gamma A, and then we increase from A to B. And for example, then at position T, let's say, if that is position T, then here we are at position gamma, we get the point gamma T on the curve. It's a bit like you'd take a ship cruise along some river, maybe the Rhine River, and it tells you, this is kilometer 50 on the Rhine. So you got a parameterization of a curve. Now, obviously, conceptually, in order to understand curve integrals, the very first topic is we need to understand curves. So we need to understand curves in the first place. So we need to first define these as geometric objects and then discuss them a bit further in detail. All right. Let's talk about curves. What is a curve? So, for the purpose of this class, a curve is a function. It's just that. It's defined on an interval. Let's call the curve gamma, little gamma. And it's defined on some interval from A to B. And it goes into n-dimensional space. And the parameter is always called t in this class. We take t and we map it to some point gamma t. We may think, you don't need to, but we may think of gamma t as a position at time t. Sometimes that's helpful, sometimes it's less helpful, but maybe as a starting point it's helpful for you. We may think of gamma t as like the position on this curve at time t. So again, we have got some curve in space. We start at position gamma A. We finish at position gamma B. And every point on this curve is associated with some t. So we go from an interval from A to B. And generally speaking, we can now parameterize the curve. Okay, that's a geometric setting. Let me also settle some notation. Namely, we make a distinction between this function, little gamma, which takes the interval and maps it onto the geometric object. And on the one hand, on the other hand, we've got the geometric object, which we call big gamma, which is the curve. The image of the curve, gamma, is written big gamma, another Greek letter. So we make a distinction between these two objects, like this parameterization, little gamma, and then the geometric object that we have in space is called big gamma. That will be important occasionally. That is what we mean by a curve. Let's do two examples for that. The first one is super simple. Let's take gamma going from 0, 1 to 1. And let's say it maps into R to the 3. We take this parameter t and we map it onto the following. Let's say, for simplicity, 2 plus 3t, 1 plus 2t, and 5 minus t. That describes a straight line between 2 points. It's super simple, just a straight line from, well, at t equals 0, got 2, 1, and 5. And at t equals 1, we go straight on a straight line, and we arrive at the following 5, 3, and 4. Just a straight line in three-dimensional space. Another curve that looks familiar to you is the unit circle. Let's say a curve gamma, and the interval, the parameter interval, is from 0 to 2 pi. It maps into two-dimensional space. And we take the following positions. For any t, we take cosine of t and sine of t. That's just a parameterization of the unit circle. So we start at position 0. We start at position 0. We arrive at position pi half, pi, 3 over 2 pi, and eventually we come back to 2 pi. So you've all seen this picture already. It should look familiar to you. So it's just a standard parameterization of the unit circle that you've seen before, I think. Of course, there are more complicated examples as well. In particular, we would like to settle also a bit of terminology before we proceed. So we are interested in curves that have certain properties. For example, we want differentiable curves. We would like to have curves that do not cross themselves. In fact, the very first example is a straight line. It goes from some point to another point. The second example, the unit circle, is a closed curve, which has the same endpoint as the starting point. That leads to the following terminology. Namely, we call a curve gamma, which goes from A to B into R to the n, which has components. Well, it's a vector, so it has got n components. We call those now gamma 1 of t, and so on, gamma 2 of t until gamma n of t. And we introduce the following terminology. We call it simple if gamma does not self-intersect. So what does it mean? Basically, it does not cross itself. And formally, that means the following, namely gamma going from the half open interval A, B is injective. The notation here means T is greater equal A, but strictly less than B. You might have seen different notation for these half open intervals depending on the class. Then, as already mentioned, another very important feature that a curve might have, it's closed if the start point is the same as the end point. The straight line is simple but not closed. The unit circle parameterization is simple and it is closed. Okay, those are some geometric features. There are also some features that are related to differentiability. So obviously, we would like things to be differentiable to work with them, since we're doing calculus. So we call a curve differentiable if the n components, gamma 1 up to gamma n, are differentiable. So very straightforward. And finally, the last piece of vocabulary here, une courbe régulière. A curve is called regular if the following: if it is differentiable, and in addition to that, we always have the following: the time derivative of the curve is never completely zero. So a curve is called regular if all the components are differentiable and at no point in time, at no position, are all the derivatives equal zero. There's always some derivative that's non-zero. So in fact, it will be very important to discuss these derivatives of curves, because there's another geometric concept. We will come to a few examples to discuss these concepts, but before, there's one thing I would like to introduce, which is quite important, namely the tangent vector of a curve. It's something we encounter again and again. So it's very important to be aware of that definition. The tangent vector of a curve, gamma, is the following. Well, the curve needs to be differentiable. Let's say of a differentiable curve. All our curves will be differentiable. It's defined as follows. Namely, the time derivative of the entire curve is just the vector of all the derivatives in each component, for each component. Got the derivative of gamma 1, derivative of gamma 2, and so on, up to the derivative of gamma n. That's the tangent vector, and there's a quantity related to that. And the speed is just the magnitude of the tangent vector. So you all remember the magnitude of a vector. It takes the square root of the squares of the entries. So we sum up derivative of gamma 1 square plus derivative of gamma 2 square up to derivative of gamma n square. And of that sum, we take the square root. Just the magnitude of the tangent. The tangent, well, it's a geometric concept, and it can be visualized as follows. Let's suppose I've got a curve. At every point in time, at every position, I mean, let's say here I've got the position gamma t. Then the tangent can be visualized as follows. It's a vector. It's literally tangent to the curve. And it tells you, okay, what is the direction where the curve is going and how fast is it going. The longer the vector, the faster the curve is moving. For example, here it would be this, like this, and so on. Before we go into the break, let me just write down one more possible definition of the tangent vector, which relates to something that you've seen in analysis 1 and 2. Namely, we can also express a tangent vector in terms of difference quotients. Let's say, do it like this. We can define it as follows, similar to the definition of derivatives via difference quotients. We can write gamma t. The derivative of gamma t is a tangent as a limit as h goes to 0. One more minute. Gamma t plus h minus gamma t divided by h. Just a standard difference quotient that you already know from analysis 1 and 2. Basically, it's just like you apply the difference quotient to each component. That can be visualized as follows. Suppose again we got a curve. And let's say we've got gamma t here. And somewhere else we got, a bit further, we got gamma t plus h. If we let h go to 0, if h approaches t, and if we take this difference, this is gamma t plus h. If we let h go to 0 and divide this vector by h, then eventually we get the tangent vector at gamma t. All right, with that we go into the break. And after the break, we will take a look at a few examples for that. All right, so we have had a bunch of definitions now. We have had now a bunch of definitions related to curves. So we have discussed simple curves, closed curves. We have had the notion of differentiable and regular curves. And very importantly, we have introduced now the concept of tangent and speed. So this concept of the concept of the tangent will encounter us again and again throughout the next weeks. And before I did the break, please correct this one T here. It's a right bottom. I wrote an H, but I meant to write a T. If you take this difference quotient and you distribute the limit over each component, in some sense, you just get all the difference quotients that you already know from analysis 1. Okay, with all that being said and done, let's proceed with a few examples. The most simple example that we can talk about, except perhaps for straight lines, is a unit circle. So we got our parameterization of the unit circle from 0 to 2 pi, going into the two-dimensional plane. We take t and map it to the cosine of t sine t. Okay. The first thing we would like to take a look at, what is a tangent vector? The tangent vector gamma point t equals, we just take the derivatives in each component, minus the sine of t and the cosine of t. Now, if I try to visualize this now, which is a good idea, it's always a good idea to visualize things. Okay, I got my parameterization, my curve, going into the counterclockwise direction once around the origin. And if you just plug in a few values, what you will observe is that these vectors look as follows. Very much what you would expect. It points in the direction where you're going, and it's always tangent to the unit circle. And besides, as we're on it, what is the speed? Just 1. Is it a simple curve? Who says it's simple? Please raise your hand. Okay. Yes, thank you. It's simple, and it has got the same starting point as the endpoint. Gamma A is the same as gamma B, so it's also closed. And, well, it's differentiable and regular. All very good. Okay, simple closed curve, differentiable and regular, a parameterization of the unit circle. Let's take one more look at a slight variation of that. I'll try to do something similar. Gamma goes from zero to k pi into r to the 2. And other than that, it's the same formula for the vector field, for the curve. T is mapped to the cosine of t and the sine of t. K, well, there's some constant, can be 2, 1, 2, 3, 4. Okay, what would this look like geometrically? So we're taking steps on the circle. Okay, here, this is for k equal 1. If k equals 2, we can get further around. Now, if we proceed with that, k equals 3, k equals 4, etc. Basically, we end up taking half-circle steps with circle around the origin. Okay, I can spoil as follows. It's differentiable, and it's regular. Is it simple? Is that a simple curve? The answer may depend on k. For example, for k equal 1, I take a half circle step. Is it simple? Yeah? Is that still simple? Is it simple for k equal 2? Yes? For k equals 3, what happens? Perhaps somebody can tell. Yeah, please.
It makes half a circle more.
Yeah.
But I don't know if that's still simple because it doesn't intersect.
Well, it does intersect itself because it overlaps.
Yeah.
So it very much intersects because if you circle around once, let's do the laser pointer. You start here, k equal 1, k equal 2, and now, well, it has overlap with itself, so it's no longer simple for k equals 3. It has very much an overlap. Yeah.
But with k equal 2, we overlap at the end.
Okay, the point? Simple. Let me write down again the definition of simple. It's a good detail to be aware of. Simple means that gamma from the half open interval A up to excluding B is injective. So A is included, but B is no longer included. And that avoids the problem. Yeah. Is it closed? Okay, for which values of k is this a closed curve? Perhaps there are suggestions. Yes, please. Even? Yeah. So even, if it's even, like 2, 4, 6, 8, then it's closed. Because if k is even, we always end up with a full circle. If k is odd, we always end up on the other side. So if k equal 1, we end up on the other side. K equal 2, okay, we do a full circle. K equals 3, k equals 4, and so on. Okay. Let's cool down a bit and do something super simple again. Let's just do the straight line, just for good practice. Let's suppose I've got a curve parameterized over 0 to 1, going into r to the 2. And let's say this time we take 2, 1 plus t, 1, 3. So in other words, to be super explicit, gamma t equals, it just takes the sum of these two guys, gamma plus t. Gamma t equals 2 plus t in the first component, and 1 plus 3t in the second component. Okay, taking now the derivatives in each component in t, we get very easily the corresponding formula for the tangent vector. The tangent vector is just 1, 3. If we draw this in a coordinate system, we start with the point T1, and we end up at 3, 4. The tangent vector in this special case is really just a straight vector going from the starting point to the end point. That would be a bit different if I would have used a different parameterization, but that will be on the exercises. Okay. It's just for good measure, let's also say, yes, it's differentiable, regular, it's simple, but very obviously it's not closed. Obviously, we end up somewhere else than where we started. Okay, one more example before we discuss curve integrals. In fact, let's do it as follows. Gamma goes from, let's say, 2 pi gamma goes from the interval from 0 to 2 pi into r to the 2. That's the parameterization of the curve. And let's say we map t onto the following point. Each point on the curve is t and 2 plus sine of t. So this will look a bit like a drunken driver, namely as follows. The starting point is 0, 2. And the curve will, well, we proceed with speed 1 in the x direction, but we oscillate in the x1 direction, but we oscillate in the x2 direction. Basically, it looks as follows. Okay. What is the derivative? What is the tangent vector? The tangent vector is gamma t, the derivative of gamma t. Well, in the first component, it's just 1. And it's in the second component, it's a cosine of t. Okay, let's suppose here is 2 pi, here is pi, here is pi over 2, and let's say here we have got pi over 3. 3 pi over 2, I mean. 3 pi over 2. Okay, we can plug in the formula for the derivative, for the tangent vector, and plug in the vectors. What is that vector? At the very beginning. Zero, 2. No, not the position. What is the tangent vector here? Someone has a suggestion? It's very simple. Yeah.
1, 1.
Just 1, 1. You see, okay, it goes in the x and in the x1 and the x2 direction. Then we reach this plateau. And indeed, the vector now is 1 and 0. Then everything goes down, and we go to the vector at this point will be, well, at this point, I mean, will be 1 minus 1. And again, we reach this plateau, 1, 0. And up here, we are again at 1, 1 in the limit. The limit will be 1, 1. Okay, it's not closed, but it's a simple curve. It's differentiable and regular. In fact, regular can also mean that the speed, regular can be expressed as follows. The speed is never zero. In fact, what is the speed? Remember, the speed is the magnitude of the tangent. So we have got the square root. We just take the tangent vector and compute the magnitude, the size of the vector, the length of the vector. And we get 1 plus cosine t squared. Okay. Of course, there are many more examples you can discuss, and those will be discussed on the next, well, the exercise sheet for next week. Okay, we have settled curves now. We have introduced all the relevant geometric concept for curves, and the whole point of doing that was to prepare a preparation for curve integrals. So basically, our goal is to integrate functions now over curves. And that is the second part of this, curve integrals. And I think it's the best idea is to start with something you already know, namely integrals over intervals. You have already seen that. We want to integrate a function, f, over an interval from a to b. So certainly we have got an interval. Interval from a to b. And we got some function. The whole point is to find the area below the curve. So the integral from a to b of f. Now let's describe an integral over a curve in a two-dimensional setting. Let's say I take my x1, x2 plane, take this plane, put it flat on the ground, and I've got a curve. Let's say from gamma A to gamma B. And on this x1, x2 plane, there's a function living. There's a scalar field that lives on this x1, x2 plane. And I would like to get the following area. Namely, okay, I take a look, what are the values of that function as it lives on the x1, x2 plane? And I would like to know this area. The area between the function values and the curve itself. So imagine I got a curve here and some function, and I would like to know what are the values between what is the area between the function values and the curve. That is a geometric step, the conceptual step, as we move now from integrals over intervals to integrals over curves. Now, generally speaking, in order to make sense of that in a mathematical, rigorous sense, we need a mathematical description of curves. We've already seen that. We've had this parameterization of curves. And now we use this parameterization of curves to make rigorous sense of these integrals. Namely, what we want to define is the integral over the curve gamma f dl, that is the integral of f over gamma. Okay, that is the goal. And for that, we use the parameterization of the curve. So, Let's start as follows. Let gamma from A to B be a curve. And let f be a function that lives on R to the n. Let it be a scalar field. F is a scalar field that lives on R to the n, produces a real number. Then the following. The integral of f over gamma is the following quantity. I write the integral over big gamma f dl. That is defined as the integral from A to B of f after gamma t, multiplied with the speed of the curve, dt. To be very explicit, it's the integral from A to B of, let me write it like this completely, f of gamma t, and then times the square root. That is the definition of the speed. The square root of the derivative of gamma 1 t square, and so on. We sum all this up to the derivative of gamma n t square. So that is the definition of the curve integral. The good thing is that, okay, we have defined the curve integral now in terms of some function over this interval from A to B. Now it's only an integral over A to B. So we have reduced this to this notion of integral that we already know. And I think the most complicated thing might be to get an intuition for the role of the speed here in this formula. So we've got the speed here in this formula. And I suppose for most people, experience tells us this is a major thing that people need some time for to comprehend. So let's talk a bit about that, a bit more detail, before we go to examples. So we have got the definition of the curve integral, f dl. The integral over gamma of f dl, that's defined as the integral from A to B, f after gamma t, times the speed at any given parameter t. Now, why do we put the speed in there? The idea is as follows. The curve integral should only depend on gamma, on big gamma, like the curve in space, but it should not depend on the parameterization t. It should not depend on the specific parameterization gamma. The parameterization is only a mathematical tool. What we're interested in is this curve big gamma. And it will take some time to get used to that, but I hope the following is helpful. Where gamma is slow, gamma t will also be slow. The speed of the curve will be small. And on the other hand, where gamma is large, where gamma is fast, the speed will be large. So if I've got a curve and with some parameterization, it might be that this parameterization rushes through the curve at some points and will be very slow in other areas of the curve. What now happens is the following. Fast sections, if I rush through something, then the speed will, well, I rush through it, it will only be a small part of the parameterization, but the speed will be very large. Then these will be emphasized in the integral because the speed will be larger. Conversely, slow sections will be de-emphasized. The effect will balance out, and in the end, no gamma dependence. Okay, maybe I should do one drawing here on the blackboard. Let's say I've got a curve. And the integral I want to take should not depend on the parameterization. Now, it might happen that depending on the parameterization, I might move through some parts of the curve very slowly. So the integral will have a long section in the slow area, but that is compensated by the speed being very slow. So that will be a long section of AB, but the speed will be slow. The speed will be small. So this long, even though the section will be very long, the speed will be slow. And if I rush through something, this will be a short section of AB, but the speed will be larger to compensate for that. I will add that as a drawing to the slides. So the effect is that by incorporating the speed, in the end, these effects balance out, and I get something that does not depend anymore on the parameterization. So I think for now that's something to think about. So let's proceed with an example. Let's do the following example. Something super simple, of course. Namely, we start with, let's suppose I've got a function f of x equal 1. Yeah, please. Okay, f is a function. So what does the function f represent? Let's say, what does the function f represent? It depends. Okay, it's a scalar field that lives on r to the 2 or r to the 3. And the curve gamma describes the path. And the curve gamma describes the path, and you want to know how much of f do you get if you travel along that path. Let me first do some numerical examples, and then perhaps in the last minute I'll make something on the board. So let's just do some calculations first. We have some function f that is constant 1. Given one simple thing we already might have seen, given any curve, big gamma, with parameterization, let's say, gamma from a to b, the most simple case is the following. The integral of over big gamma of f dl. Just plugging in definitions now gives us the integral from a to b of the magnitude of the speed itself, nothing else. And that just happens to be the length of the curve. In fact, mathematically, that's the definition of the length. The length of the curve is defined as the integral of the speed for any given parameterization. One instance, for example, fx is still equal 1, and let's say gamma t equals the curve from 2, 3 plus, starting at 2, 3, and then we take plus 1, 1, t times 1, 1. Then we integrate over f. We integrate f over gamma, and that curve integral goes from 0, 1 up to 1, and the speed is just the length of this vector 1, 1, which is we integrate from 0 to 1 the square root of 2, which of course gives square root 2, which just happens to be the length of the straight line between the points 2, 3 and 3, 4. Let me finish then, okay. Let's do some more complicated examples next time. Let me finish then with perhaps some physics example. So let's suppose, I will add this also as an extra slide. So let's suppose we move through some two-dimensional area. Suppose we move through R to the 2, and unfortunately, the two-dimensional plane is full of radioactive radiation. Let F, or let's say that instead of radioactive radiation, let's say F describes rainfall intensity. We move along a path. Let's say we move along a path, let's say from 0 to 1. That's the interval, how we parameterize the path, with constant speed 1. Let's do that for simplicity. Then this integral over gamma of f dl, which is defined as, well, it's the integral from, in this case, 0 to 1, 0 to 1 of f gamma t times the speed. Well, the speed in that simple example equals 1. Well, physically, that integral will describe how soaked we are, how much rainfall do we get at the end. How much rainfall we have endured along that path. Now, what is the role of the parameterization? Last minute. Here I've assumed, okay, we move at constant speed 1. If we change the parameterization of the curve, then we also need to take care of the speed. We need to take into account that speed. That's the most simple example I can think of right now. And we continue the discussion then on Thursday.